Hello, my name is Janet Callahan, and this is part 2, where we are learning a little bit more about bonding force curves. In this one, we're going to be focusing on bonding force curves and their relationship to bonding energy curves. All right, so let's begin with a little bit of review. We learned last time that if we are considering the bonding between two atoms, they can be the same size or they can be different sizes. That we learned that there's a bonding force curve shape, that classic bonding force curve shape that comes on up through a net bonding force of 0 in a linear fashion, and then goes off to infinity on the right-hand side, where again we are plotting net bonding force versus distance, and we are considering the equilibrium between the equilibrium bonding length between two atoms. And so that equilibrium bonding length would be the radius of the first one plus the radius of the second one, and so we would end up with this particular distance, which was the net bonding length. All right. Because, if you remember from physics, energy is equal to the integral of force with respect to distance, we can also state that dE dx is equal to F. And so where the bonding force is 0, right, which is at this location there, that's let's call it x0. At that point, we would expect the bonding energy curve to be 0. In other words, if I, beside this net bonding force curve versus distance, I draw a bonding energy curve versus distance, what I'm saying is that at this position of x0, we would expect there to be an energy minimum. Because, right, the slope would be 0 at an energy minimum. This slope, dE dx, would be equal to 0. All right, so what does the rest of the curve look like? It comes in high, kind of comes down to that minimum. And then the interesting part about this curve is that it's asymmetrical, and it moves to the right faster than it came down. And I hope you can see that from the way I've drawn that. And this is an important feature. Let me just write down, notice that the curve of E versus X is asymmetrical, moving to greater distances more slowly than to the left or shorter distances. So what I'm saying here, right, is that it's coming in steep, it's moving off to the right in an asymmetrical fashion. So why does this matter? The reason this matters is that this gives rise to our understanding of the coefficient of thermal expansion. And I'm going to talk through this, and then I'm going to we'll solve some problems in part 3. Okay, so another way of thinking about this bond energy curve, and let me just redraw it down below so I have a little more room. So we're talking about the bonding force curve, and we've understood that it reaches a minimum, it moves off asymmetrically to the right. This minimum occurs at the equilibrium spacing between two adjacent atoms. All right, so we can envision this as kind of corresponding to 0 Kelvin, right? At 0 Kelvin, there'll be no thermal vibration occurring between these two atoms. And again, these two atoms are part of a big lattice. They're not vibrating in isolation, but for the purpose of this discussion, we'll just imagine them vibrating with each other. So at 0 Kelvin, very little vibration, no vibration, right? At higher temperatures, at some temperature T1 greater than 0, there's going to be vibration, and between the atoms, they'll vibrate across different energies in this energy range that I've just drawn with the bar. And as we move to greater temperatures, let's move to an increasing temperature of T2 and now to T3, where 0 is less than T1, which is less than T2, which is less than T3, you can see that we have increasing amounts of vibration. All right, so the point I'd like to make is that if we try to imagine the midpoint, or the so what is the midpoint of these curves? Well, the midpoint of 0 is right there. The midpoint of that one's here. The midpoint of that point between there and there is here. The midpoint of those 2 points is here. And I hope you can perceive that with increasing temperature, the midpoints are kind of slowly veering off to the right. And so the midpoint represents the average distance between the atoms. And so the asymmetry of the curve explains why materials expand when they are heated. So I'm just going to write that down because it's an important conclusion. The asymmetry of the E versus X curve explains why pretty much all materials expand when heated. All right, I hope you understand this, and it's been a pleasure sharing this with you.